Let's examine the HSRP process and see exactly how a client is integrated into this overall process. Examine PC1. It has the IP address 192.168.1.10. Our routers R1 and R2, which are multi-layer switches, have been configured with IP addresses in the same subnet that PC1 is in. Using SVI, switch virtual interfaces, for example, interface VLAN 10, they have been configured with the IP addresses 192.168.1.2 and 192.168.1.3. So let's say we're using the subnet mask of /24 on all these devices. They would all be within the same subnet in this case. However, we will not point the clients to the IP addresses associated with those SVIs when we are using HSRP. We configure our HSRP group, and in this example, the HSRP group is group 1, and that is very significant, as we'll see here shortly. When we create that group with the command standby1 IP, we specify the virtual IP address at that point, so 192.168.1.1. And this is the IP address that is shared between the routers that are participating in that HSRP group. It's also going to be the IP address that is the default gateway. So all of the PCs in that subnet end up with that IP address of 192.168.1.1, which is the virtual IP address for the HSRP group, as their default gateway address. So what happens now when the client needs to send a packet out of their subnet? For example, PC1 wants to contact the server in this case. The server is not in the same subnet. So the client realizes that it must send an ARP request to find the MAC address associated with the IP address of the default gateway. Because when it creates the frame for the local area network, it has to address it with a destination MAC address of the default gateway. But do we want R1's MAC address that is associated with the SVI? No. Do we want R2's MAC address that is associated with the SVI? No, we don't. We want the virtual MAC address associated with that default gateway IP address. So this is the MAC address right here, 0000C, which stands for Cisco, 07AC, which stands for HSRP version 1. So this is the well-known HSRP MAC address. And then at the very end, you see 01. Well, 01 represents Group 1. This is how HSRP is able to have multiple groups running and ensure that the clients get the MAC address associated with the correct group, which is associated with the correct virtual IP address. So for example, if we had Group 2, the last two digits would be 02. So the final two hexadecimal values represent the group number. So can you guess right now as to what Group 10 would be? What would Group 10 be? It would be 0A, because A in hexadecimal equals 10. So Group 11 would be B, 0B. Group 12 would be 0C, and so on and so forth. So since we have two hexadecimal values that we can play with, starting at 00 and going all the way to FF, we could have 256 HSRP group numbers. 00 equals 0, and FF equals 255. So 0 to 255 is 256 possible group numbers. So the client sends the ARP request. And remember, our ARP request is broadcasted. So it's flooded out all ports on ASW1. R1's going to receive it as well as R2. But who responds to that ARP request? We don't want both devices responding to the ARP request, just one. it will be the active router that responds to that ARP request. So it says, hey, you can use this MAC address of 00000C07AC01 based on the ARP request that was sent. So the ARP reply comes back and PC1 places that information in its ARP cache. R2 will not respond to that ARP request in this case because it's the standby router. Now, if a failure occurs, for example, we have R1 that disappears, or we have the link that disappears here, then R2 takes over as the active router. And when R2 takes over as the active router, it will now be responsible for responding to the ARP requests for the MAC address of 192.168.1.1. But think about the topology from a layer 2 switching perspective. Before the failure occurred, the MAC address that is associated with the virtual router was learned on this switch interface here. So that way there, when frames arrived at ASW1 could forward those frames successfully to R1 based on the entry in the MAC address table. So when R2 takes over, as the active router, it sends out a gratuitous ARP on the network. That way there, the switches can update their MAC address table and now associate that virtual MAC address with these interfaces right here instead. So the gratuitous ARP that the new active router sends out is going to help quickly converge the MAC address tables on all of the switches, so they're now pointing to the right router that is acting as the active forwarder at that point in time.